Alright, so I haven't made a video in a little while here. Uh, we're starting off Unit 2 here. Finally starting to talk about forces and dynamics, specifically as the unit of study that's going to look at what causes objects to move. So we've looked at kinematics already. Kinematics is the study of how things move, like their velocity, acceleration, displacement, and dynamics is what makes that movement happen. So, first thing to write down is what dynamics is. It's the study of the forces that cause objects and systems to move. And then the just generic definition of a force is just that it's a push or a pull, which is a very good place to start. Now, as we've mentioned before about forces, we didn't really define them yet, but now we really are, because we have to. And forces are vector quantity, just like velocity or acceleration or displacement are. They have a magnitude, quantity to them, and then a direction as well that will be what the sign is telling us. Is it moving in a negative direction? Is it moving in the positive direction? That's really what we're going to start to look at. And then down the line, we'll shift and take a look at it in terms of at an angle as well, just like we did with 1D and 2D motion with kinematics. So here we have, these are the ways we represent forces. So the first one on the left here is just a general drawing of what's happening here. We have some ice skaters pushing another ice skater two different directions. Those directions come together and then form what's called the resultant vector, right? Just like we saw before. And in this case, that resultant vector is a force. So just like the other two forces come together and make a force here. And then we have what's called a free body diagram. Now, on the AP test, we are going to need to be able to draw those. That is something that they will be looking for, specifically in the free response questions. They will be looking for us to draw at least one free body diagram in there. So, and here's an example of one here with just those two forces that are acting upon this one skater. And that's just what the forces look like in general. We would then use Pythagorean theorem to find that resultant force that's acting upon that skater. So, didn't draw that one because here we are with the definition of a free body diagram. So a free body diagram is a technique used to illustrate all the external forces acting on a body. And go ahead and sketch this image of a free body diagram as well. Now this one's a very simple free body diagram. We'll see some that are pretty complicated later on that have forces acting at angles. We have to look at the components of that in order to figure out the net force acting on an object. So net force is really what we're going to call the resultant force acting on something. So here we have a question. The force acting on an object or system that originates outside of an object or system is called, and of course it is outside of the system, so that outside kind of guides us. It is an external force. So restoring force is something that's mostly focused on things that are being stretched or compressed, and then they go back to their original shape whenever they are not being stretched or compressed. And so one main thing that you think of when it comes to that is springs, for one. So here we have an example of that with a spring scale. So these are not used as often anymore, but we do still have them. We do still use them. And they have a regular relaxed length, that's the X there in picture A, and then it is stretched to some length, delta X in B, and then that is your restorative force that's acting on it, causing it to stretch that distance. And so at that point, it is feeling that force, and they use these in what are called spring scales that are set up to where you pull at a certain distance and it reads out a analog there scale that is telling us what the magnitude of the force is that's being applied to that object. Um, Now they make various versions of them. They have ones that have different scales on them based on how strong the spring is. And we will look more into springs and spring forces later on. But what really determines how strong a spring is something called a spring constant. And that's going to help tell how strong a spring is, how much force is going to be needed to stretch it a certain distance. And so the stronger the spring, the more force needed. And then you can create a spring scale that maybe has a larger scale on it than, say, the one we have pictured here that just goes from 0 to 9. So just varies depending on how strong that spring is that they use. They also need to make sure that they pick ones that aren't going to stretch out over time or just not go back to that restored shape, because otherwise, if that happens, then you're not getting accurate readings anymore, and that could be a problem. So we did not do this, but you're welcome to if you want to. Get an idea as to how a rubber band and paper clip can show those things. So with dynamics and with forces come Newton's laws of motion, and this is our first one of these, Newton's first law of motion. So Newton's first law of motion, I'll highlight this here for you. It states that a body at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted upon by a net external force. Now, there is another way to think about this. So Newton's first law of motion is also that there states that there must be a change, so a net external force, for there to be any change in velocity. Remember, change in velocity means acceleration. So really what that's telling us is that in order for there to be a change in motion, there needs to be a change in velocity, which means there needs to be an acceleration, and a force must be that cause of that change in velocity or change in motion. So friction is always going to be something that's going to be counteracting our motion here. We aren't going to define it here because we will define it later on. But we just do have to keep in mind that friction is there. We are going to have some instances where we're going to say it's negligible, we're going to ignore it, and we're going to try to keep with that as much as we can. But it is something that really does happen, and it does not make it so that we have to use calculus like air resistance does. So we are going to be able to use things with friction, and friction is just another force. It's just a specialized force that counteracts the motion. So Newton's first law of motion states that. Which one of these is right? A says a rate of change of momentum of a body is directly proportional to the applied force of the direction of the force. We have not talked about momentum at all yet, so A can't be it because it's talking about something we haven't even talked about at all. B is a body at rest remains at rest, or if in motion remains in motion at a constant velocity unless acted upon by a net external force. That sounds right. That is it. That is B. That's our answer. That's the first law. And then C here, just to look at it, when one object exerts a force on another object, the second object instantaneously exerts an equal and opposite force on the first object. Now that is one of Newton's laws, but it's not the first one, and it's not one we've talked about yet, but we will. So some applications of Newton's laws. So just going to kind of glaze through this here, but basically Newton's first law is completely general and can be applied to anything. Objects sliding on a table, a satellite in orbit, or to blood pumping in the heart. Experiments have thoroughly verified that the change in velocity, any change in velocity, speed, or direction, right, that is a change in velocity. Even if it's just direction, that's still a change in it, which means there is an acceleration occurring. Must be caused by an external force. The idea of generally applicable or universal laws is important not only here, it is a basic feature of all laws of physics. Identifying these laws is like recognizing patterns in nature from which further patterns can be discovered. So Galileo, back in the day, who really actually developed this first law, and then Newton, who then clarified it and made it into what it is, they asked the question, what is the cause of something occurring in the natural world? Whereas in ancient Greece, typically, they wouldn't ask, what is the cause? They would say, well, that's just the nature of the beast. Like, so they have the example here, why does a tiger have stripes? That's the nature of the beast. That's how it is. No, it's not. That may be true. That may be correct as well, but it's not the answer we're looking for. Right? It's not helpful. So, what is the cause of this change in motion? Well, forces are the cause of the change in motion. So, Newton's first law of motion was actually discovered by, and that, of course, is, as mentioned in the last slide, Galileo Galilei. Of course, hopefully everybody knows who Albert Einstein is. Did a lot of things in physics. Theory of relativity is the main thing. Everybody likes to throw out E equals mc squared anytime they think about physics. But he's the one that did that. Michael Faraday did something called a Faraday cage. He did several things, but this is the main thing that's got his name on it. But basically, he showed that if you were looking at charge, like electric charge, on a metal shell, it will stay outside of that metal shell. So, for example, in a lightning storm, the safest place to be is inside a car because the lightning charge will stay outside, not affecting you. It may affect the electronics in the car, but it's not going to come in and hurt you. As long as you're got the windows up and aren't touching everything on the dash and everything possible. It may go through some of the electronics that way, and your car probably is going to be totaled, but at least you will survive and not feel the effects that a true strike of lightning would do to you. And then we got D there, Niels Bohr. If you don't know who he is, maybe you need to take a trip back to chemistry class. But Niels Bohr is known for the Bohr model of the atom. Question 2 here, which of the following is not an example of Newton's first law of motion? I'm not the biggest fan of this question, but they say that the answer is really hitting a ball by a bat, because really both of those things are in a state of motion that's changing as it is, so there's really not an external force going on there. I don't know, it's weird to explain, but to me that is an example of it as well, and really all these could be seen as an example of it depending on how you're saying it's an example of Newton's first law of motion. It's just a weird question, but we'll kind of skip over that one. Alright, so mass and inertia, which is our next thing we need to define. So the property of a body to remain at rest or to remain in motion with constant velocity, which should sound familiar. That is Newton's first law of motion. So, therefore, we call Newton's first law of motion the law of inertia. It's a nice, easy way to remember what Newton's first law is. It's the law of inertia. And as long as you remember what inertia is, you should be good. Now, we also have what inertia of a body is measured by its mass. So, mass, of course, the definition of that is the measure of the amount of stuff or matter in something. And then one thing we haven't talked about yet, units of all of these things. So the SI, our standard unit of mass, is the kilogram. Or kg. And the SI unit of force is the Newton, or just a capital N to represent that. Now notice I did not capitalize the word Newton, because if you're referencing it as a quantity or a unit of something, you don't capitalize it, which is kind of new to me. I've always capitalized it, but because it is named after a human, a person. So it's debatable, but apparently that is the way it's supposed to be. When we get to energy, you'll see joules. Joules is also going to be the same idea. So what is the relationship between weight and mass? They are not the same thing. I'll tell you that right now. Weight is a force, right? We just talked about what the units are, right? Weight is a force, which means the unit is newtons. Mass is mass. It is in kilograms. They are not the same thing. And when we get to Newton's second law, we'll even see more about how they are not the same thing. And the intrinsic unchanging property of the body, that's going to be mass, right? Mass doesn't change. You can go to the moon, you can go to space, you can go to Jupiter. Wherever you go, your mass is going to remain the same. However, the weight, or your weight, will change depending on where you are, because weight is dependent on gravity. It's also known as the force due to gravity. So, if I go to the moon, where gravitational pull is 1.67 around meters per second squared, that's going to change what my weight is then, because my weight is depending on how big the gravity is at that place where you are.